most of the thyroid cells are arranged in follicles. On the microscope, they'll look like rings because we're just slicing through it, but they're actually hollow balls. Inside each one is a substance called colloid that stores the hormones until we need to release them. Then there are some cells between the follicles. I think that's a couple of them up there. There's some here. Those are called C cells, and they're going to release different hormones. And we'll see these today in lab. From the follicle cells, we get the thyroid hormones. Their names are thyroxine and triiodothyronine. Thyroxine just means amine from the thyroid. We call it T4 because it has 4 iodines attached to it. Triiodothyronine means the thing from the thyroid that has 3 iodines. So this shows each of them. They're made from an amino acid called tyrosine, and they're actually built right in a protein. And a second tyrosine gets its ring put on, and then the iodines are attached. And while it's stored in the colloid, it's in the protein. We release it by cutting up the protein to release the hormones. Thyroid hormones speed up metabolism. Specifically, they increase breakdown of carbs and lipids. In children especially, less so in adults, they actually stimulate protein synthesis. And that uses some of the energy that you're getting from breaking down the carbs and the lipids. From the C cells, we get calcitonin. And that, from the first part, you can tell is going to have something to do with calcium. What it does is lower the amount of calcium in the blood. I said that twice, didn't I? So, the 2 ways it does that is by telling your osteoblasts in the bone to build more bone, to store that calcium. But also by telling the kidneys, oh yeah, we got plenty of calcium, you can just let it go in the urine. So we don't hold on to calcium like the precious resource it seems to be these days. Oddly enough, we are kind of frugal with sodium, which we have plenty of. So those are some things that show you how our bodies aren't quite adapted to modern conditions. So a way to remember calcitonin's action: tones your bones, makes your bones stronger by saying store more calcium in them. The parathyroid glands are around the back of the thyroid where those 2 lobes wrapped around. This shows the trachea and the esophagus. So thyroid doesn't completely close around them, but it comes around the back a little bit. The parathyroid glands are a couple of little nodules on the back. Most people have 4, but some might have 6 or even 8 separate little lumps. They only make one hormone, so we just called it parathyroid hormone. The job of parathyroid hormone is to oppose calcitonin. So if your calcium's too high, you release calcitonin and that lowers it. If your calcium's too low, then you release parathyroid hormone that increases it. It does that 3 ways. 2 of them are the opposite of what calcitonin does. It tells the bones to release the calcium. It does that by telling the osteoclasts to break down some matrix. It tells the kidneys to hold on to the calcium. And it also stimulates activation of vitamin D, another thing that happens in the kidneys. Vitamin D is actually a hormone that's going to act on the small intestine and tell it to absorb more of the calcium from your food. This is why a lot of calcium supplements also have vitamin D in them, to make sure you've got that there to tell you to absorb that calcium. Okay. Questions on thyroid and parathyroid? I do have a little summary on blood calcium. So if it's too high, calcitonin. If it's too low, parathyroid hormone. This flow chart just shows the parathyroid. We act on the bone to release the calcium, act on the kidneys to conserve the calcium, and through the kidneys and vitamin D, act on the intestines to absorb the calcium. And then as the levels increase, we inhibit PTH release. And we'll see something similar coming up with glucose. Right. Adrenal glands. The name means near the kidney or on the kidney. They're sort of triangular, sitting on top of the kidney. And if you slice inside, there's two layers. The cortex and the medulla. We saw these terms used with the brain. You had the cerebral cortex, that was the outer layer. The medulla oblongata, which didn't look to be inner when you were looking at the brain by itself, but you had the cerebellum behind it and other parts of the head in front of it. It's fairly well insulated. And we'll see several more organs throughout the semester that have a cortex and a medulla. Cortex means rind, so it's always the outer part of something. Medulla makes adrenaline, which is not a medical term in the US, although it is in Britain. I'm not sure why we decided to go with epinephrine instead. I'll talk about that coming up. The cortex, the outer layer, makes the steroid hormones. And if you can get a really good look at it on a slide, there's 3 different layers of the cortex that have a little different texture to them, and each one makes a separate hormone. So we'll start with the medulla. There's a group of chemicals it produces that are called catecholamines. The major one is epinephrine. There are some catecholamines that are also used as neurotransmitters, like dopamine. Epinephrine is the major one used as a hormone. Norepinephrine is mostly a neurotransmitter, but a little bit hormone. They're each made from one amino acid, and they're made kind of in a series where you make a couple more changes as you go, and that's what gets you a different molecule. I don't have a slide about the word origin. Okay. So, we call this an adrenal gland. Anyone know what a kidney doctor is called? Not quite. Neuro is nerves.
Adrenologist.
It would be a good guess, but what we usually see is we use Latin for parts and Greek for clinical situations. Like ologist is Greek, so we use the Greek word for everything with that. Nobody remembers?
Is it nephro?
Pretty close. Nephro. And epi is Greek for on. So the gland gets the Latin name for being near the kidneys. the hormone gets the Greek name for being near the kidneys. And then that nor part is just specifying that it's a variation on the molecule. So what epinephrine does is prepare the body for emergency or a stress situation. It mimics the sympathetic nervous system. So anything you might remember from the nervous system about what sympathetic does, epinephrine is going to do a lot of those same things. You've probably heard fight or flight. I like to use the 4 E's because fight or flight just goes with emergency. I'm in danger, I have to either fight back or run away. But you get a lot of the same effects with other situations like excitement. You're going on a roller coaster. Maybe you're a little scared that you might fall out of it or something, but you're not like running for your life unless you're really afraid of things. Embarrassment does some of the same stuff, like your heart beats faster. And exercise, I think, is actually one of the easiest ways to think about what might the sympathetic nervous system do. Is a change that happens during exercise is probably going to be the same thing for sympathetic. Like it inhibits digestion, it increases the heart rate. Epinephrine also has 2 metabolic effects, which are to increase the blood glucose and speed up the cellular respiration. It does number 1, so it can do number 2. And that gives your muscles more energy to contract with if you are jogging or running away from this big scary bear. Questions on the adrenal medulla? Adrenal cortex has 3 hormones. They're all steroids. Technically, it's 3 groups of hormones, but I'm picking one major one from each group. And the abbreviations for those would be SAC. S is for sex hormones, which is mostly androgens. That means man makers. Testosterone is a very strong androgen. These are the reason that after menopause, women might see some more masculine changes like going bald or losing or getting facial hair, is those fill in for the missing estrogens. Before menopause, we think the androgens might be involved in sex drive. The A is aldosterone. That stero part is because it's a steroid. Aldosterone is part of a group called mineralocorticoids. The corticoid for coming from the cortex. Mineral because they affect mineral balance or electrolytes. Aldosterone specifically tells the kidneys to retain sodium and excrete potassium instead. The amount of sodium brought back from the kidneys determines how much water gets reabsorbed from the urine. So as a result, aldosterone will also stimulate water retention. It increases your blood volume. Aldosterone also stimulates some other hormones that constrict blood vessels. So this is another one that could apply like ADH if you were dehydrated or had lost blood. The third is cortisol. Its group is called glucocorticoids. So each of these 3 also ties in with something that starts with S and people usually want more of than they need. Sex, salt, and sugar. So, a little more on cortisol, since it's the most complex. Cortisol is more for dealing with extended stress. So where epinephrine is, here's this danger right now. Cortisol is something going on longer term, like having an injury or an infection or just being cold for a while. The big thing it does is increase the availability of glucose, and that's helpful for your muscles if you need to shiver, your immune system if you need to fight an infection, the cells that are repairing an injury, and so on. So it increases the glucose availability by inhibiting protein synthesis, except for the specific cells that need to do it. It tells the liver to put more glucose into the blood, both by breaking down glycogen, your storage form, and by making new glucose out of other molecules. And it stimulates breakdown of fatty acids instead of the glucose to feed the cells that can use it. It also inhibits inflammation, and this is to help, inflammation is a useful effect in a certain area that has an infection, but you don't want it to spread too far because it can cause damage of its own. So the cortisol helps keep it in check. So if anyone's ever had steroids for an infection or